All right, welcome back. Here I am. So the last lesson was 8.5. We did the following objective. We learned how to determine the limiting reactant. We learned how to calculate the other terms below that, the theoretical yield, actual yield, and percent yield. Well, this lesson we're really going to be doing the same thing. So all I did was change the 8.5 to an 8.6. And I put a little star there with the phrase dealing in grams, because hey, in everyday life, that's what we're going to be dealing with is grams. You're going to be putting stuff on the scale. You're going to see how much grams you have of it. You're going to see what its mass is, in other words. Once you know something's mass, then you can convert that to moles, because you really need to know how many moles you have, because the recipe's in moles. In 8.5, that's all we talked about was moles, moles, moles. The word problem always gave you moles. Well, your scale's not going to give you moles. I'm sorry. So you're going to have to convert from grams to moles so that you can analyze your recipe and analyze the relationships between those reactants and products in that chemical equation. And then you're going to need to convert it back to grams, because you're probably going to be doing something with that information. And so you're probably headed right back to the scale to either check your work or keep moving forward. And oftentimes in chemistry, when you finish one reaction, you're just getting ready to start the next. And so that being said, let's dive right in. And I also just realized, guys, that I forgot to give you lesson 8.3, which is all about grams too. And so I think what I did is I filmed it and I realized it was blurry, and I either deleted it from the Google Classroom, took it off. So hopefully none of you guys watched it because it was atrocious. Or I deleted it before I even put it on. I'm not sure, but it was blurry, and I've got all my tech issues figured out, so I think I'm ready to go with a bunch of videos. Now, I'm going to backtrack, give you 8.3, because it's a really important lesson that sandwiches what I've already given you, the 8.1 to 8.3, and then the 8.5. It's right in the middle there. 8.4 it's a big one. It's a big one. It also deals with mass, and so please maybe try not to watch this one or even 8.5 until you watch 8.3 if you're seeing all this at once. But I've already put 8.5 up about in a couple hours ago. So if you've watched that, you could probably watch this one and be good to go. But then make sure you backtrack and watch 8.3. I think that'll help you with a lot of your homework problems. And then there's really only one more section after that. So what I give you tonight should carry you through the weekend and a lot of next week. So if you don't get any videos from me for a while after the few I send you tonight, just chew on these and schedule them at your own pace so that it's convenient for you to manage your own time and such. And make sure you're staying on top of the homework problems. As far as labs go, I did find a really good virtual lab on the PHET Colorado website that we use for simulations. It's an activity real similar to one you've already done, but it's related to this limiting reactant. So I think you'll enjoy it. Actually, it'll really help you understand this. And then I have one more lab I'd like you to do at home with actual ingredients in your kitchen and stuff like that. And so that'll be the next week probably. So the first thing I want to look at is this conceptual checkpoint. Let's just make sure we understand this before we jump right into 8.6. Consider that reaction there, nitrogen gas. I'm going to read it like I should. 1 mole of nitrogen gas plus 3 moles of hydrogen gas will produce for you 2 moles of ammonia gas. Okay, ammonia is NH3. If you look at that flask to the left, and let's say that represents the mixture before the reaction, okay, that's the mixture before the reaction, so you can count the molecules you see there. Which flask below, A, B, or C, represents the products after the limiting reactant has been completely reacted? So first of all, what is the limiting reactant? Can you tell by looking at that flask there on the left? Okay, can you tell by looking at the flask? Well, you couldn't tell if you didn't know the recipe. You have to look at that flask alongside that recipe. So looking at the recipe, noticing that 3 hydrogen gas molecules, which are diatomic by the way, are going to react with every 1 nitrogen gas molecule, which is also diatomic. So it's like a 3-to-1 ratio. Every time we use 1 nitrogen molecule, we're going to use 3 hydrogen molecules. Okay, so we only have 2 nitrogen molecules. So every time we use 1 of them, 3 hydrogen. That's all we have in the flask too, is 3 hydrogen. So let's look over to the right. And it looks like C is the answer. But you might be going, wait a minute, how did we go from 5 molecules, period, total, of stuff in the left flask and only 3 in the right? Well, it's because the atoms get redistributed. Remember, we're making totally brand new compounds. And if you count the atoms, you can literally count 1, 2, 3, 4 blue ones, and 1, 2, 3, 4, 5, 6 white ones. That's what we have on the left. And so basically all the white hydrogen molecules got used up, and we just have 1 nitrogen molecule left over, unable to react with anything. Poor guy. And so basically you can see what's going on there. And that's kind of what the lab simulation I'll give you will do. It'll allow you to like kind of see the molecules, make a lot of that make more sense. But so you can see the molecules, you can see how many moles. So we say how many moles, but in this case, you could actually count the molecules. And same thing, you're just scaling everything. You're scaling the recipe down to molecules, basically, is another way you could do this. But we're really going to shift gears here, and this might throw a lot of you off. And we're going to be giving numbers instead of in moles. We're going to be giving them in grams. Because check it out, nitrogen gas weighs, even though nitrogen gas and hydrogen gas are both diatomic elements, they both weigh completely different, right? Their molar masses are completely different. The molar mass for hydrogen atoms are 1, so for a hydrogen molecule, it would be 2. Nitrogen is 14, so for a nitrogen molecule, that would be 28. So 28 versus 2, that's a pretty big difference in grams there. 28 grams versus 2 grams per mole, that is, right? So grams per mole. So the molar masses are going to have, so if you say, I got 400 grams of hydrogen and I've only got 200 grams of nitrogen, well, that doesn't mean you have more hydrogen, because hydrogen doesn't weigh very much to begin with. Actually, no, I'm saying I said that wrong. If you had 400 grams of hydrogen, you'd be in good shape. If you had 400 grams of nitrogen, that wouldn't be so impressive if you were trying to say how much more you had of nitrogen than hydrogen. And let's say you only had like 300 grams of hydrogen. Well, that would actually be a lot of hydrogen, because compared to the 400 grams of nitrogen, it's the molar masses that would make a difference. So when working in the laboratory, they just reinforce what I said. We normally measure the initial amounts in grams, and then to find the limiting reactants and theoretical yields from initial masses, we must add 2 steps to our calculations. So we're going to add 2 steps to our calculations. Consider the following synthesis reaction. Kind of a classic example here of sodium and chlorine gas coming together to make sodium chloride. So solid sodium, let's read that recipe. 2 moles of solid sodium coming together with 1 mole of chlorine gas will give you 2 moles of sodium chloride. All right, so what would we do after we've been given this problem? Let's say that in the lab you measured out that you had 53.2 grams of sodium, and you also had a flask of chlorine, and you were able to know that you had 65.8 grams of chlorine. What is the limiting reactant? And what is the theoretical yield? So you're going to begin by sorting the problem out, by writing down what's given to you. So if you make a nice little list like that, that's good. So you can pull those out of the word problem. You've been given 53.2 grams of sodium, and we've been given 65.8 grams of chlorine gas. And we want to find the limiting reactant. Well, just like we did in 8.5, you basically need to figure out how much product each one of those reactants will give you, all by themselves independently. Okay? And so, like, what's the maximum amount of sodium chloride that sodium will give us? What's the maximum amount of sodium chloride that chlorine will give us? Based on the amounts that we have, of course. And so if you scroll down there, you can see that they've got a long solution map. A purple box to a green box to a yellow box to a red box. Okay, we're going from box to box to box to box. Why are we doing that? Well, basically we're going from sodium to sodium chloride. That's really essentially all we're doing. And on the bottom, we're going from chlorine to sodium chloride. So we're still going from just a reactant to the product. And on the bottom, we're going from a different reactant to a product. Same product too, by the way, sodium chloride. And so the problem is, it's just we're going from grams of the sodium to moles of the sodium. And then we're going from moles of sodium to moles of sodium chloride But then finally, we also want to turn that moles of sodium chloride to grams of sodium chloride. So basically, you're going to start with grams of sodium, because that's what was given to us. And they said it was 53.2, right? Here's our solution. I kind of ignore all this other stuff. Well, I don't ignore it, but I can talk about it as we go through the solution. We started with 53.2 grams of sodium. So you see that written down there at the bottom under the solution. They've got just 53.2 grams of sodium there by itself, starting the problem. They don't put that over 1 like I normally do, but whatever. I like to see it as a numerator, to be honest with you. They immediately then are going to want to see how many moles that is, because again, the recipe's in terms of moles. So our final goal is sodium chloride. But in order to get to sodium chloride, we need to first get to moles of sodium so that we can go from moles of sodium to moles of sodium chloride. And so to go from grams of sodium to moles of sodium, that's just simply molar mass, right? Anytime you have a conversion factor with grams and moles in it, that would be molar mass, right? And the relationship is that 1 mole of sodium is 22.99 grams of sodium. You guys remember where to find that number? It's on your periodic table. On your periodic table, you'll find the molar masses of elements. Okay, now that we're in moles of sodium, we can go to our recipe. We can go to our chemical equation up here, which is our recipe. Our chemical equation over here, which is our recipe, which says, remember, we're going from sodium to sodium chloride. So what's the relationship? 2 moles of sodium for every 2 moles of sodium chloride. And so there you go. You can see 2 moles of sodium on the bottom of that conversion factor and 2 moles of sodium chloride on the top of that conversion factor. I'm looking at the third one there. Well, the third fraction, but the second conversion factor technically. And you can see that that's getting us out of moles of sodium and putting us in moles of sodium chloride. Now, if I stopped there, I would technically know how much sodium chloride I could make, given the amount of sodium I have. But I would rather know how many grams of sodium chloride I could make, because at the end of the day, I'm going to have to give that answer in grams. And so I could just take the molar mass of sodium chloride, which is 58.44, and make a conversion factor. 1 mole of sodium chloride is equivalent to 58.44 grams of sodium chloride. Look how that intentionally is set up so that moles of sodium chloride cancels, and that grams of sodium chloride is the last unit left up on top there of that last conversion factor in the fraction. And then it equals, after you crunch all the numbers, 135 grams of sodium chloride. That's how much table salt you'll make if you were given 53.2 grams of sodium. And remember, this is assuming that you have plenty of chlorine to go around. All right? We're going to do the same thing now, starting with the chlorine gas that we have. If we only have 65.8 grams of chlorine gas, and we assume that we can use it all, how much could it theoretically give us of table salt? How much could 65.8 grams of chlorine gas make for us in terms of table salt, the product? Well, just run your conversion factors. Go from grams of chlorine to moles of chlorine, moles of chlorine to moles of sodium chloride, and then moles of sodium chloride to grams of sodium chloride. If you're watching this video and you haven't watched the 8.3 video that I'm about to make as an afterthought, trying to squeeze it in there, you might want to watch that one first, because it's going to show you how to go through all of these conversion factors that we're doing now. All right, we're doing a lot of 8.3 in this video here, but we're doing it for a different purpose. We're doing the work, but then what we're doing is we're analyzing this work, and we're seeing, okay, well, the sodium, that particular amount of sodium at least, will make us 135 grams of salt. That particular amount of chlorine gas will make us 108 grams of table salt. And so which one's going to be our limiting reactant, the sodium or the chlorine? Well, do you remember how to tell? It's the one that makes you the least amount of product. That's the definition for a limiting reactant. You should drill that into your head. It's a limiting reactant because it limits how much product you're going to make. It's the reactant that limits how productive basically your chemical reaction is going to be. All right? Your limiting reaction is kind of the sad story. It's the sad news. It's the one that's going to break your heart because it's only going to allow you to make so much material. Unless it's something deadly, then you would hope that the limiting reactant would run out quick so that enough toxic gases wouldn't be produced or whatever. But in this case, it's that 108 grams of salt, right? And so guess what? Our chlorine is the limiting reactant. You don't have to say how much. You just say that it's chlorine. But when you get to the theoretical yield, of table salt, you do need to give that in terms of a number. You need to give a number. And remember that the theoretical yield is dictated by or is determined by what limiting reactant you have, and of course how much of that limiting reactant you have. And in this case, the amount of chlorine gas that we have is only going to allow us to make 108 grams of NaCl. You can see it there highlighted in yellow. Okay? And so you might be saying, well, what was the point of doing all that work above it for the sodium? Like, we're not going to use any of those numbers. Like, we have 135. We did all that work to solve for the fact that we're going to make 135 grams of salt, but we're never going to use that number in our answer anywhere. So what bunch of pointless work. It wasn't, because how did you know you couldn't have made less? You know, maybe the sodium could have only allowed you to make 100 grams of salt. Well, in that case, the sodium would have been the limiting factor or the limiting reactant. So you actually have to do both trials, run them both so that you can do the comparison, and then you're going to kind of toss all the other work and just keep the work that you have that you know is involving the limiting reactant. All right. Oops, sorry. I got to change screens here by doing this. Okay. I'm going to do two more examples here. But let's finish the one we're doing right now. Good. I was hoping they would do this soon. Okay. Now suppose, see how they're giving you a little hypothetical situation here? Suppose that when the synthesis was carried out, okay, that the actual yield of NaCl was 86.4 grams. What is the percent yield? All right, well, I'm glad they didn't ask for the actual yield, because that would just be kind of like, what's it kind of like called whenever you ask for something that's super obvious? Like, really? You're going to ask that? They literally told you that the actual yield is 86.4 grams. That's usually not really actually asked of you, unless you're in lab. It's going to require you to give the actual yield of what you get. But in this case, they had to tell you. So to get the percent yield, remember, you just take what you actually get over what you theoretically should have got if you did everything right. But again, in chemistry, it just doesn't work that way. A lot of substances get lost in translation. They get lost in the filtering process. They get lost in the transferring of substances from one apparatus to another, and through thermal decomposition, it gets boiled off or what have you. And so we only made 86.4 grams out of 108. Well, that's kind of like almost like a test score. It's almost out of 100. So you'd say it's around a B, right? Around a B. And sure enough, it's 80%. It's 80% after you do 86.4 divided by 108. Okay, you remember how to find the percent yield? It's the actual yield over the theoretical yield. Just like you would try to figure out your percentage on a test. You just take what you got out of what you should have got, what you actually got out of what you theoretically should have got. And then, of course, you do have to times it by 100 if you want to express it as a percent. Okay, finding the limiting reactant and theoretical yield again, just through another example. Okay, we're just going to find the limiting reactant and the theoretical yield. Here's a neat equation, and this is going to help us learn something new. They're throwing us a little, I wouldn't say a curveball, but a slider. It says ammonia, NH3, can be synthesized by the reaction. By the way, that was the reaction in this beaker here, in this round bottom flask that we kind of analyzed in the conceptual checkpoint. We were synthesizing ammonia, NH3. If you look at that beaker on the right there, you'll see the nitrogen with the 3 hydrogens. That's ammonia, and that was synthesized using nitrogen gas and hydrogen gas. But this reaction is slightly different. You're taking hydrogen gas and nitrogen monoxide gas, which is still possible. And you're going to make ammonia gas and water. So you're actually going to make 2 products. And that's I was telling you, not quite a curveball, but I would say a slider maybe. they're giving you two products. So which one do we want to consider? Let's see. It asks what maximum amount of ammonia in grams can be synthesized from 45.8 grams of nitrogen monoxide and 12.4 grams of hydrogen. So they straight up told you, how much ammonia can be synthesized. But if they were just to ask about the limiting reactant, they wouldn't necessarily need to even tell you which product they're interested in. You could just pick one. Pick one and actually just run the math on each reactant and see how much of that product it'll make, and you can figure out what your limiting reactant is. But in this case, they're being very direct and saying, hey, what's the maximum amount of ammonia? So we'll take each ingredient. We'll take the 45.8 grams of monoxide, and we'll take the 12.4 grams of hydrogen, and independently we'll carry those numbers, we'll carry those values through a series of conversion factors that eventually give us an answer in grams of ammonia. And we'll compare them. We'll compare them, and we'll look for one makes the most. No, that would be a dream world. We're going to be looking for the one that makes the least, so that we can be real, we can be practical, okay? We can be realistic, because whichever one makes the least, that's unfortunately all that we're going to be limited to being able to make, right? Keyword limiting, limited reactant. So you can see the solution map there. You don't have to do that solution map, because look, they're basically just writing out a bunch of conversion factors that you're inevitably going to use down here below in the solution. So let's just go straight to the solution. I like to save a little time here. The first quantity that we knew we had of a reactant was the nitrogen monoxide. So if you take that 45.8 grams of nitrogen monoxide and you run it through that series of conversion factors, which again, if you're lost on how and why we're going from grams to moles to moles to moles and moles to grams, watch the 8.3 video, because it's going to really go into detail of that map. And I even give you a map that you can refer to, so that you know why, so that you can always use it. But let's know why. Again, we're starting out with a certain amount of nitrogen monoxide in grams, but our recipe's in moles, so we're turning that into moles of nitrogen monoxide. And then that's what that first conversion factor does, is turn it into moles of nitrogen. And that's again so that we can look at our recipe. Once we look at our recipe, we can find the relationship between nitrogen monoxide to ammonia. But again, that's in moles, so that's why that second conversion factor there is 2 moles of nitrogen monoxide to 2 moles of ammonia, which is really just a 1-to-1 ratio, so that actually not going to affect our answer numerically. But look, that takes us mathematically to a different unit. Now we've gone from talking about how much nitrogen monoxide we have to basically talking about how much ammonia we have. So if we stop here, we literally know how much ammonia we have. But let's take it one step further and figure out how much grams of ammonia we have. So using the molar mass of ammonia, which they've done the dirty work for us, and it's 17.04 grams. That's the molar mass of ammonia. You won't find that on the periodic table, but you will find the molar masses of the elements that make up that periodic table, or that compound on the periodic table. So just add those up, and that's what you'll get. Then finally, just crunch all those numbers, and you'll see you get 26 grams of ammonia. Well, doing that same process, but just with the other reactant, which is the hydrogen, specifically the 12.4 grams of hydrogen, you'll see that in the end you get 41.8 grams of ammonia. Well, how much ammonia are we going to make? I wish it was the 41.8, but unfortunately, that's again living in a dream world, because the 45.8 grams of nitrogen monoxide is going to be limiting us to only making 26.0 grams of ammonia. And so nitrogen monoxide simply is our limiting reactant, and the theoretical yield of ammonia then is just going to be 26.0 grams of ammonia. That's going to be our theoretical yield. That's theoretically how much we should make, and if all goes well. But of course we know again that it doesn't always go well, and so sometimes they'll give you an actual yield. Again, they'll tell you to find or determine the percent yield, but they haven't done that in this problem. They just wanted you to find the limiting reactant and the theoretical yield. So here's another example. We don't have to do the skill builder. let's go to this one because they will make us do the percent yield again, and they give us another chemical equation. And here's one that is sorry, I was got distracted. Here's one that provides us an example where there's a curveball, I would say, not just a slider, but a curveball. We have two products on the right, but they don't really ask us necessarily about any specific product. Check it out. It says, consider the reaction. 1 mole of copper oxide plus 1 mole of carbon. Let me say that again. Let me start over. 1 mole of copper oxide plus 1 mole of carbon mixed together, probably in the presence of heat, I would imagine, will make or produce 2 moles of copper and 1 mole of carbon monoxide gas. So let's read the problem, because that's just the recipe. That's not the problem. When 11.5 grams of carbon are allowed to react with 114.5 grams of copper oxide, 87.4 grams of copper are obtained. Ooh, a little extra curveball there. They're actually telling us how much of a substance we make. It says find the limiting reactant, the theoretical yield, and the percent yield. So what have they given us in the problem? They've actually given us 3 numbers again. Remember, they gave us the initial amount of ingredients that we're starting with exactly to their exact quantities. But they even gave us that 87.4 grams of copper that's produced. So we'll jot that down. And then the way to solve this is essentially still the same. You're going to take your reactants and you're going to run them through those series of conversion factors. Look at that solution map again, by the way. Look at this solution map. The purple box to the green box to the yellow box to the red box. What they're doing from there is they're basically going from carbon to copper. Down below, they're going from copper oxide to copper. So our final goal is copper, right? That's what we care about, is copper. And we're just starting with different reactants, though. And to do that, to get from the reactant to the product, you just have to go through those conversion factors that basically take us from grams of the substance to moles of it, and then from moles of that substance to moles of another substance. That's kind of the beauty right there. When you're in moles, because you have that recipe, you can literally set up a conversion factor that takes you not just from like a different measuring unit, because it's just mole to mole. It's a mole to mole relationship. And so our units go from mole to mole. Like we don't really change units, but we do change unit because it's moles of one substance to moles of another substance. Again, that's the beauty of it, because we're literally figuring out now how much copper we can make. But we take it one step further just to figure out how much grams of copper we can make by using the molar mass of copper. And we look at both trials there, and we'll just go straight to the answer here, or the solution, I'm sorry. You can see them working out the problem here. They put in the numbers. They put in the 11.5 grams of carbon to start with, and they ran it through all the conversion factors so that they would end up in grams of copper, and they got 122. They took the 114.5 grams of copper oxide that we also start with, and if we were to use it all up, how much would we theoretically make of copper? Well, there you go. It's 101.7. So we have 2 different scenarios. The carbon's going to allow us to make 122 grams of copper. The copper oxide is going to allow us to make 101.7 grams of copper. So which one is it? Do we want to be optimistic and brag and get all excited about the 122 grams of copper? No, not yet, because according to what we have at our disposal, that 114.5 grams of copper oxide as a reactant is going to be a limiting reactant, because it's only going to allow us to make 101.7 grams of copper. So realistically, that's what we're theoretically going to make. And that's literally what you call it. That's the theoretical yield of copper. Okay? And so to finish off the problem, you have to remember that they said we were able to make 87.4 grams of copper. So really the reason they gave you that number was so that you could figure out this percent yield. So theoretically, we should get 101.7. Okay, just like that's kind of what you should get out of an exam if it was worth around 100 points. So basically, whatever we get in grams is going to be pretty close to our percent because our denominator is so close to 100. We got 87.4 grams. Okay, imagine getting an 87.4 out of 100 on a test. You'd be getting about an 87%, right? So like a B plus. It's a little less than that though. After you crunch the number and multiply by 100, you get 85.9%. So, okay, that's actually going to be it for this lesson. Told you that was quick. I'm hoping to actually, make these videos quick to watch, but allow you time to do the problems and kind of go through your own struggle. You learn when you kind of go through your own struggle and then ask questions and find solutions in the book, or just working hard and finally figuring it out, or getting on Zoom during my 30-minute sessions and getting help there, or asking a classmate. But that's the best way to learn. So I'm hoping you're really getting practice with the homework problems. Let's look at this conceptual checkpoint. I really like these. I think these are good. It says the ammonia gas can be, they love ammonia gas, don't they? Oh, here they go. They gave us that same equation, didn't they? Ammonia can be synthesized by the reaction of nitrogen monoxide and hydrogen gas. By the following equation. Is that the same equation? Sorry, I'm sidetracked here. I'm going back to, it is the same equation. 2 moles of nitrogen monoxide plus 5 moles of hydrogen gas make 2 moles of ammonia and 2 moles of water. So they're using the same equation there. But without doing the math, that's why this is called a conceptual checkpoint. Like without doing the math, do you conceptually get how to solve this problem like in your head? It says a reaction vessel, it could be a flask or a beaker or whatever, initially contains 4 moles of nitrogen monoxide and 15 moles of hydrogen. What is in the reaction vessel once the reaction has occurred to the fullest extent possible? All right, so basically 2 nitrogen monoxides will come together with 5 hydrogens. Okay, and what do we have? We have 15 hydrogens and 4 nitrogen monoxides. So we're going to use up, so how many groups of 5 do we have of the hydrogens? That's the way I'm seeing it. You guys might see it a different way. But how many groups of hydrogen do we have in 5s? Because we use up 5 at a time. We have 3, right? Because we have 15. So 5, 10, 15. So we're essentially going to be able to make 3 moles of ammonia, assuming that we have 6. Assuming that we have 2, 4, 6 nitrogen monoxides, but we don't. We only have 4, don't we? So technically, we're going to be able to use up that's going to be our limiting reactant, is the nitrogen monoxide. And since we only have 2, since we only have 4, and we use 2 for every 5, we're basically going to use the 5 twice, right? So 10 hydrogens, and we're going to use up all the nitrogen monoxide. And so the only answer for all the nitrogen monoxide is B or D. And you can see B says you're using up both nitrogen monoxide and the hydrogen, so it's not going to be that one. It's going to be D, because they're still leaving you left with 5 moles of hydrogen left over, and that's essentially what would happen. If you use 10 but you started out with 15, you'd still have 5 moles of hydrogen left over. Pictorially, how do you see that? That's coming up in the next video, so stay tuned for that. I'm going to show you that simulation on PHET Colorado, that website, and kind of walk you through what I expect of I'm just going to use it as a teaching tool, and then I'll have you do the screenshot like you always do of your 5-star results there. Thanks for watching. Till next time, so long.